Hello, welcome back. I just started recording. We're now going to move into our homework. Hey, Peyton, what's up, buddy?
What up?
You ready to do some homework?
Yes, sir.
Okay, me too. Let me get a pretzel here, and then we could go. I just remembered that I had some pretzels too, and I want to be in the gang. This is pretzel hummus combo, so whoa, dope. Okay, do you guys have a book handy, or do you need me to get mine? I'm in the club now. This hummus ain't looking too good. I think it's got mold. In fact, I'm not sure I should be eating any of that. Okay, let's do some homework. Yeah, it's bad hummus though. Okay, I got my textbook right here. Do you guys have the numbers? You got the numbers for me? Someone shout a number at me. What's our first one?
50.
I'm sorry, one more time, Kayla?
50.
50. All right, Kayla, would you be down to read that one?
Yep, it's called solar energy output.
Hold on a sec, let me get all queued up here. Okay. Don't forget to put your names and stuff. Chapter 14, problem 50, solar energy output. Okay, take it away. Yeah, can you throw all that out? Oh, thank you. That's even better. You are awesome. Jordan just brought me some good hummus. Yes. Okay.
It says, observations over the past century show that the sun's visible light output varies by less than 1%, but its X-ray output can vary by a factor of 10 or more. Explain why changes in X-ray output can be so much larger than those in the output of visible light.
Okay. So before we get going here, I've got a thought question for the class. What does the sun produce more of? X-rays or visible light? Does the sun produce more X-rays or more visible light? Simple enough, right? No one?
Did we discuss that it was X-rays?
We discussed X-rays, but we did not discuss that it was X-rays. The sun does not produce more X-rays than visible light. Perhaps we need to look at the spectrum of the sun, seen as a plot. Allow me to share screen here. Allow me to find a particular slide. You know, if we looked at the spectrum of the sun, we would see an absorption line spectrum. In fact, we did look at the spectrum of the sun. And when we did this, function F554, we saw a rainbow with dark absorption lines. Jace.
Doesn't it emit all wavelengths equally?
It does not. It does emit all wavelengths, but it does not emit all wavelengths equally. I'm going to do something. I'm going to turn this spectrum of the sun, which is a rainbow with absorption lines, into a plot, kind of like the one that you see here. But I'm not going to just do it for visible light. I'm going to do it for the entire spectrum, the electromagnetic spectrum. This is what a modern spectrum looks like for an astronomer's point of view. It's a plot of wavelength on the x-axis and intensity or brightness on the y-axis. Here you'll notice the absorption lines look like little dips in the so-called continuum. If you do this for the entire sun, this is the plot that you get. This is a plot of the intensity of sunlight as a function of wavelength from like 100 nanometers all the way to 2000 nanometers. Where does visible light fall in the spectrum, class? Where does visible light fall on this spectrum? I'm asking a simple question, I think. This is wavelength in nanometers, right?
400 to 700. Or
Yeah.
800.
So this is your visible domain right there, right? Where would X-rays fall on the spectrum? Where are X-rays in comparison to visible light?
Less than 400.
Yeah, like they're like somewhere over here, right? They're less than 10 nanometers, so actually they're kind of like there. So what does the sun produce more of? Visible light or X-ray light?
Visible.
Right. Yes, the sun is a black body, and yes, Jace, black bodies produce all wavelengths of light, but do they produce all wavelengths equally? Hell no. In the case of visible light, your peak is here, right? In the case of X-ray light, the amount they're producing is like down here somewhere. Clearly, there's a lot more visible light being produced than there is X-ray light. So what does the question ask then? What's the question asking us? Because at first I thought they were saying, why does the sun produce 10 times more X-rays than visible light? See, I can't really give you the answer to the question unless you understand the question. And I'm a wee bit concerned about that. Talk to me,
I thought
kids.
the question was asking how much those wavelengths vary.
It's the variability. Excellent. Yes, sir, that's exactly what my point is. Let's make a little graph of this together. It's the variability over a century. So I'm going to start by making a little graph. Put this in your notes. This is part of your answer. And let's do a plot of brightness on the x-axis, brightness in watts per meter squared. And this is now going to be a function of time in years. And we'll go from, say, 1900 to 2000. This is a 100-year period. Because we could see that there was a lot more visible light, I'm going to use black for visible wavelengths. We'll keep the visible light up here with only a slight wiggle at the 1% level. Okay? So that's what the visible light is doing. The visible light from the sun stays roughly constant with only small wiggles. But the X-ray light, which I will demonstrate in purple, is lower in intensity but highly variable. So what we'll see is spikes in X-rays followed by dips in X-rays, especially following the solar magnetic cycle that happens over 11 years. With the peak in X-rays at the top being a factor of 10 times greater from maximum to minimum. Now 10 is kind of like a decimal number. It's a factor of 10. Whereas in the visible light portion, we have 1%. Class, what does a factor of 10, oh, actually Laura in particular, because she's not my new percentage expert. Laura, what does the number 10 translate to as a percentage?
The number 10?
Yeah.
Is it not 10%? No.
10 times is not 10%. That's my point.
I have no idea. I don't know why I don't.
What is the number 1 as a percentage? What's the number 0 as a percentage?
0%.
Okay, we're that good. How about 0.5? What's that as a percentage?
50%.
Okay, what's the number 1 as a percentage?
100%.
What's the number 10 as a percentage?
1000%.
Now you're talking.
Yeah.
Factor of 10 is 1,000%. That means relative to visible light, X-ray light is 1,000 times more variable. There's a factor of 1,000 times greater variation in X-ray light than in visible light. Okay, so what's the answer? Now that we understand the question, we can proceed to answer it. Why is X-ray light so variable, 1,000 times more variable than visible light? It's got to do with layer and it's got to do with process. Well, where's the bloody visible light produced?
Photosphere.
Okay, good. Where's the X-ray light produced?
The upper atmosphere layers.
In particular, which one?
Oh, the corona, right?
Yeah. Okay, what processes produce visible light?
The rising and falling of the granules.
Well, the granules deliver the light, but that's not what makes the gas shine. What makes the gas
Fusion?
shine? Pardon?
Fusion?
No.
Fusion?
Fusion isn't what makes this gas shine. And this gas shines the same way the photosphere does. Well, this is a chemical reaction, but you're missing my point. Look at your notes. I wrote down what makes the photosphere shine in your notes. I got to get rid of these pretzels. They're bad juju. They're just stale. Thanks. Thanks. Oh, geez, guys, I feel like I'm at the dentist here. Because I'm pulling teeth. What?
Thermal black body radiation?
That's right. This shines by thermal radiation, black body radiation. This is thermal radiation. What makes the X-rays shine in the corona? Let's look. Let's look at some corona X-rays. Let's go to slide 3 or 4 or 5, whatever it is. Okay, this image, this video shows you the intensity of X-ray light coming from the corona. Where do we see the greatest emission in X-rays? Where are the X-rays the brightest?
Near the magnetic field lines.
Yeah, and especially where the magnetic field lines get densest, closest together.
Where they're
That's how we-
twisting up.
Well, the twisting and the bursts, watch when you see a solar flare, then you see a huge burst in X-rays. So we had a name for this type of radiation. It's called Bremsstrahlung radiation. It's when plasma strikes the magnetic field lines. Okay, I think we're ready to put all this together into an answer. Let's start here together. X-ray emission from the sun can be so much more variable than visible light emission because X-rays are produced at different layers and by different processes. And now we'll go into the details on this. X-rays are produced in the sun's corona by interactions between plasma particles and twisting magnetic field lines. As the magnetic field lines vary with magnetic storms and the 11-year solar magnetic cycle, so does X-ray emission vary dramatically. So this explains why the X-rays are so variable. Let me just take a moment for you guys to catch up to that. See if I can focus. Can you guys read that?
What does that say? Plasma particles in what?
No, it's crooked.
Well, look, you mean like this?
No, like the right side of the board is cut off.
Oh, is that a focus?
No, it's just that the words are cut off. Like you have to tilt it to the right because the right side of the board, like the words are cut off. No, other way. Yeah, there you go.
They're not cut off on my screen. Are they cut off on everyone's screen?
No, I can see them. I just can't read it. It's just not.
There it is. There it is. Okay.
Talk to me, Samantha, about where you're having trouble. You said
Plasma particles in what magnetic field?
twisting magnetic field lines.
Perfect. Thank you.
Twisting. I'm sorry, guys. This fucking camera was a waste of money. Do I have the high definition tab clipped or tag? Let me go to my video. Enable high D. Yeah. All right. How are we doing here? Because we have more to add to this. We have to talk about the visible light. I'm going to erase this top paragraph. Let's address the visible light now. Visible light, on the other hand, is produced at the sun's photosphere by thermal blackbody radiation. As the photosphere's temperature remains constant, so does the emission of visible light remain constant. Can I erase a couple of lines here? Anyone going to complain?
I just finished magnetic storms, so everything, like the first 3 lines, I'm good with. If that's good with everybody else.
Thanks for the input. That helps me. Unless anyone else wants to complain, I'm going to erase the couple top lines. So does the emission of visible light remain constant with only a 1% variation due to blank. Fill in the blank, students. What is causing the 1% variation in the output of visible light at the photosphere? Let me look around the room for a victim here. I think someone's saying they want me to volunteer them. Isn't that right, Peyton? Peyton, do you want to be my volunteer? Is that what you're trying to say to me?
Writing.
What do you think could be causing the 1% variation in visible light? Maybe you need a picture.
Sunspots?
Oh, sorry?
Is it sunspots?
You are absolutely correct, sir. Nicely done. Beautiful. I'll give you guys a second to copy that while I fill up my iced tea. We're going to need to make a dangerous iced tea run. A dangerous iced tea run. Risk our lives. Sorry, I needed my vampire water here.
Hey, I have a quick question.
Yes, Ernie.
Back on that chart that you erased earlier when you had time and years, was that 1900 or 1400?
1900. Because in
Okay.
the question, Ernie, they said observations over the past century. So I just
Yep.
picked 1900 to 2000 is a nice little window, okay?
Thank you.
Anyone else have questions, or can I want to erase, but I don't know if you guys are still copying or what. Where y'all at? I can see 7 of you, and the 7 of you that I can see seem to be done writing. Okay, erasing it is. We'll move on to the next one. Board's getting a little icky. Hold on. I can dramatically increase the length of my markers and the quality of your reading by doing a quick wipe down here. This is part of the fun of being an at-home teacher. You kind of have to do it all yourself, which I'm okay with. I like that. Okay. All right, that ought to brighten up our day a bit. Okay. What's the next question?
55.
55?
Chemical burning in the sun.
Okay, Kayla, it would be a big help if you keep reading this for me. Hold on here. Okay. Read it out for me.
When an object burns in a fire, the amount of energy released through this chemical burning is typically about 10 to the 8 joules per kilogram of mass burned. Use this fact to estimate how long the sun would last if its energy source were a huge fire releasing chemical energy rather than its actual source fusion.
How long can the sun burn? You guys remember this was part of our lecture today, right? All right.
What does that say under chemical?
One more time.
What does it say under chemical? What's that?
Fire.
Oh, fire. Okay, thank you.
Sorry. You know what might be helpful for me? In my video settings, I want to, what happens if I click? Oh, this is better for me. I just flipped my screen so that I can, I always see everything backwards on my camera, but I think this is better for me. Okay, so that says fire. So we're going to need some numbers to work with this. We're going to assume some solar constants. We need the mass of the sun and we need the luminosity of the sun. The mass of the sun tells me how much matter I have to work with. And that's 2 times 10 to the 30 kilograms. That's right out of our lecture on Monday. I also can assume that I know the luminosity of the sun, 4 times 10 to the 26 watts. I'm kind of curious to see if you guys can think your way through this one independently. I'm here to help, of course, but anyone have any thoughts about how we might proceed? How we might kick this party off? How should we begin? What technique, what should my final answer have in terms of its units? What should the units of my final answer be?
Should be seconds, right?
Yeah, it should be some unit of time, and probably, considering what we have to work with, seconds. Although we'll take any unit of time we can. How am I going to take joules per kilogram, kilograms, and watts and turn them into seconds? Thoughts?
Watts are joules per meter squared, right?
Not joules per meter squared, but what are watt? What's a watt?
Is it joules per seconds?
That's right. Watts stand for joules per second. Well, that's helpful, Jace, because now I can see my units of time there, right?
Yeah.
Okay. So what do we do? What do we do? How am I going to solve this? Not sure I know what to do, guys. I'm getting I sort of forgot how to solve the answer to this problem. I got confused. What should we do here?
Can I ask for a hint?
Here's your hint, dimensional analysis.
Okay. I was just going to ask if it's a formula we learned.
Well, that kind of suggests no, right? Even if there is a formula, who cares about the formula? No, there isn't a formula that you learned. You got to use units to answer this question. Look, why don't you take all your numbers and smush them all together in such a way that you end up with seconds? There's a bigger hint. Can you do that for me?
Would it be the 10 to the 8 divided by the mass times the luminosity?
All right, let's start with that. Let's start with our 1 times 10 to the 8 joules per kilogram. And your suggestion was to multiply it by what?
No, I said divide by mass times luminosity.
If I divide this by mass, I'm going to have joules per kilogram squared. Is that what I want?
No.
So come up with a different idea.
Mass on top, luminosity at the bottom.
Okay, mass on top. Who said that? Who was that masked man?
Marcos.
Marcos, thank you. Marcos, I'm with you, bud. That'll certainly cancel out our kilograms. And what was the other thing that you suggested to do?
The luminosity at the bottom of the division bar.
Oh, I like the way you talk, son. Okay, so if I put the luminosity on the bottom, that's 4 times 10 to the 26 joules per 1 second, isn't it? How very clever of you, sir. Because then my joules cancel out here. And, okay, this sounds like a you job. Punch him up. I refuse to touch a calculator. It's below my pay grade. I'm sort of in an executive position here.
I got 5 times 10 to the 11
Units?
seconds.
All right. Hey, Jace, that's the correct answer, but what do you say we convert that to a more amenable unit of years? Does anyone remember the conversion from seconds to years? Otherwise, I'm going to make you do it in long form. How many seconds are in a year? I thought someone was cool here. Let's get that Aiden guy back on. Maybe he knows. No? No one knows the number of
31
seconds.
million?
Pardon?
31 million.
Yeah, 31.5 million. Okay, fine. The way astronomers remember it as pi times 10 to the 7 seconds, which is also 31 million. So 1 year is 3.15 times 10 to the 7 seconds. And yes, I know that pi is actually 3.14, but who cares? Okay? All right, so do the math and tell me what I got there. How many years is that?
$16,000?
Say that?
Is it 16,000 years?
Yes. Very good, Laura. Box that up. This corresponds with the quantity I gave you in today's lecture, when I told you that the sun could shine for approximately 10,000 years due to chemical reactions. So the number is actually 16,000, but I had the right order of magnitude, as they say. Cool? All right, let me just check on everyone, see how they're doing here. I'm going to scroll through my list of faces to see who's still writing. Peyton's cracking his knuckles, so he seems good. Angel, you're in the dark, so but it looks like you're okay. Got a thumbs up from. Okay, everyone's good. All right, let's move on to our next question then. I'm going to erase, and Kayla, you're doing such a great job reading. Do you mind being the reader? Okay, cool. Let me erase. Chapter 14, what's the number?
56.
Okay.
And it's called The Lifetime of the Sun.
Okay. This is where we try to convince ourselves that the sun can shine for close to 10 billion years through nuclear fusion. Read it out for me, Kayla.
The sun's chemical composition was about 70% hydrogen when it formed, and about 13% of this hydrogen was available for eventual fusion in the core. The rest remains in layers of the sun where the temperature is currently too low for fusion. Part A. Use these data and the sun's mass to calculate the total mass of hydrogen available for fusion over the lifetime of the sun. Okay.
So let's draw a little picture of this together, okay? Let's draw a circle on the board. This is the sun. And as you know, roughly 3/4 of the sun is hydrogen, and roughly 1/4 of it is helium. But none of the helium gets used for fusion. So we have to get rid of the 3/4 or the 30% that's helium. Of the remaining 70% hydrogen, not all of that hydrogen is hot enough for fusion. The only place where fusion can take place is the 13% that's in the core. We need to figure out the mass of this nugget here. We need to figure out the mass of this central nugget where it's only the hydrogen and only the hot hydrogen which can actually fuse. So this is part A. How do I get the mass available for fusion in the sun? Clearly, it's not the total mass of the sun of 2 × 10⁻³ kilograms. Sorry, I've lost focus here. Now it's, okay, here we go. What should I do?
Get 13% of 2 × 10⁻30.
Well, what about the 70% hydrogen? Yeah, Jason, that's the right idea. We're taking the mass of the sun, okay? But before we multiply it by 13%, shouldn't we multiply it by 70% to just get the mass of the hydrogen? So
Yeah.
if we take this and multiply it by 0.7, that gives us whatever fraction is in hydrogen, and then we can multiply it by 0.13%, okay? So we'll do 2 × 10⁻³ kilograms times 0.7 times 0.13. I'll take the answer anytime.
I got 1.82 × 10⁻²9.
Okay.
I got 4.2 × 10⁻²9.
Can I get a third answer for a third calculation so we can win the tie?
I got 1.8.
Sounds like 1.8.
Yeah, 1.8 and change.
I'm sorry, was it 20? What was the power again?
29.
Jace, check your answer again.
It was 29. The
Okay.
power.
Oh, no, but didn't you say you had 4 point something?
4.2, I think. I got rid of it. Sorry.
That's okay. I think I remember this being the answer. I think this is the answer. At least 2 people got it. Remember that anyone can make a mistake, and sometimes 2 people can make the same mistake. So everyone's supposed to be punching to keep us all on track here. Okay, Kayla, what's part B?
Part B says, the sun fuses about 600 billion kilograms of hydrogen each second. Based on your result from part A, calculate how long the sun's initial supply of hydrogen can last. Give your answer in both seconds and years.
How many zeros are in a billion?
9.
Kilograms per second. And we've got to figure out how long the sun can last. Did you guys learn anything in our last problem? How am I going to get a unit, an answer that has units of time? What's the technique that I'm going to use?
Dimensional analysis.
That's right. Jace, do you think you can do it?
Give me a second.
Sure. Anyone else is welcome to shout in too if they have a plan. But Jace, you can try it. You know.
Sorry, what was the question?
The question is, how long can the sun last if it fuses 600 billion kilograms per second?
All we really got to do is divide by kilograms, right? Or divide by the mass we just calculated.
Okay, so tell me what to do.
1.8 times 10 to the 29 divided by 600 times 10 to the 9 kilograms a second.
So if we do 1.8 times 10 to the 29 kilograms, and then we put kilograms on the bottom and seconds on top, in 1 second, the sun fuses 600 billion kilograms. Nicely done. Get me the answer. That's a 1, everyone.
$3.17 seconds.
3.17 seconds?
No.
That sounds kind of weird, right? Like 3 seconds.
Okay.
The sun's only going to last for 3 seconds.
I got 3 times 10 to the 17.
Oh, okay. That sounds a little better. Did you have a 17 out there, Laura?
Yeah, my brain is a little funky today, but
Don't
yeah.
forget, you got to include those 17 zeros, okay?
Yeah. I was doing 0.17 to the 17th.
Oh,
Yeah,
I see.
which was just my brain being
Yep,
dumb.
I get it. I get that. My brain's a little fuzzy too. Let's convert this to years. What's my conversion factor from seconds to years?
3.15 times 10 to the 7th.
Very good. How many years is that?
Nine times 10 to the 9, or 9.5 times 10 to the 9.
Good. 9.5 billion years. That's how long the sun can last due to nuclear fusion. There is a part C. Kayla, when you finished writing, you can read part C for us.
Part C says, given that our solar system is now about 4.6 billion years old, when will we need to worry about the sun running out of hydrogen for fusion?
So we need to compute our time left. How do I do that?
Wouldn't it just be 9.5 times 10 to the 9 minus 4.6 times
right.
10 to the 9?
And what does that give us? Anyone?
4.9 billion?
So we've got 5 billion years left. And hence, it is fair to say that the sun is approximately halfway through its lifetime. Notice you get significantly more time from nuclear fusion than you do from chemical burning, like fire. Okay, 2 left to go. Take a moment to finish copying. Are we ready? I'm erasing. Okay, Kayla, line them up and knock them back.
This is question 60, called the color of a sunspot.
Oh, this is a nice, easy one. Okay, so tell me what it says.
Use Wien's law and a typical sunspot temperature of 4,000 Kelvin to calculate the wavelength of peak thermal emission from a sunspot. What color does this wavelength correspond to in the visible light spectrum? How does this color compare with the overall color of the sun?
Okay, hold on, you gotta slow down from here. First, let's write down Wien's law. Lambda max is 3 million nanometer kelvins divided by the temperature. And then it gave us, so here's a patch of photosphere. And we have a sunspot here. What did it give us as the temperature of our sunspot?
4,000 Kelvin.
Okay. And then it wants us to calculate the peak wavelength, right?
Yeah.
So we can do that. Lambda max is 3 million nanometer kelvins divided by 4,000 kelvins. What's that give us?
$750 nanometers.
In what regime of the electromagnetic spectrum is 750 nanometer light?
Infrared.
Jace, one more time.
Infrared.
Yep. We tend to say that the visible spectrum ends at 700 because it's convenient. But actually, Jace, the human eye can see. I would accept infrared as a perfectly legitimate answer. But I would like to point out here that the visible spectrum, where are we here? The human eye can perceive close out to 750.
So it would be more like dark red.
Red/infrared is probably the best answer. It's both of those are viable answers. You can see this visible continuous spectrum goes out to 750. We usually just say 700 as our sort of default. Okay, so let's put underneath here. Let me end my share screen. Oh shoot, I want. It's weird. Sometimes it will let me change the size of this window. Sometimes it won't. Well, whatever. I guess I don't need to see all of your faces, just a couple of them. Okay, so let's put red/infrared. All right, Kayla, I'm forgetting what the rest of the questions were asking. So read the more of that again.
The last question says, how does this color compare with the overall color of the sun?
Wait, was there something else though? It asked us to compare it to something.
There's two questions. The first one, what color does this wavelength correspond to in the visible light spectrum? We just answered. So that just leaves, how does it compare to the overall color of the sun?
Okay, fine. Sorry, I thought there was maybe more to it. Normally, a patch of normal photosphere is at 5,800 Kelvin. What peak wavelength do you get if you plug 5,800 Kelvin into your Wien's law? Plug it in and tell me what you get.
(517 nanometers).
And what color is 520 nanometers?
It's like greenish, right?
Yeah.
Green and yellow.
So normally the sunlight peaks right in the middle of the green portion of the spectrum. So we could say that a sunspot light is a bit more reddish, if that's a word, a bit more reddish than the photosphere. Well, than the normal photosphere. We could compare by taking a ratio, but I don't think it's helpful here. And I think that's our whole bloody question right there. Check, see how we're doing on time. Hey, we're not doing bad, guys. We got one left to go. Kayla, does it seem, where are you, Kayla? I can't find you. Does it seem like we answered all the question then?
Yeah, it does. I think we're all set.
Okay. Class, I'd like to erase. Do I see any people still working here? No, everyone seems pretty good from what I can tell. All right, at least all the people I can see. Let's go ahead and erase this. And we got one more to go. Last question.
61. It's called solar mass loss.
Okay. So this is called solar mass loss. Hit me.
Estimate how much mass the sun loses through fusion reactions during its 10 billion year life. You can simplify the problem by assuming the sun's energy output remains constant. Compare the amount of mass loss with Earth's mass.
Okay, I intentionally assigned this problem so you guys could see that sometimes in a technical calculation here, they're asking us to sort of solve a problem without any apparent givens. They're kind of leaving it up to us to figure out what the givens are. That's very sneaky of them. So let's imagine that we were to draw the sun, and that the sun is shining and radiating away light. And somehow this light has to be coming from the internal fusion at the core of the sun. Now, when they say you can assume that the sun's energy output remains constant, they're assuming that we'll use the luminosity of the sun of 4 times 10 to the 26 watts, which, as Jace pointed out a few moments ago, is 4 times 10 to the 26 joules per second. Now, I'm going to make an argument with you here. If we're producing 4 times 10 to the 26 watts at the surface of the star, at the photosphere, then we must be producing in here at the core 4 times 10 to the 26 joules per second due to fusion. And the argument goes like this. The energy that is produced inside the nuclear core of the star will eventually leak its way out to the surface in the form of visible light. If you imagine that the sun produces more than 4 times 10 to the 26 joules per second, then somehow energy would be lost as it travels through the star. But that doesn't make sense because the star is in equilibrium, and energy can neither be created, it can't be destroyed, and it can only be created if you lose some mass through E equals mc squared. If the sun did not produce 4 times 10 to the 26 joules per second, you'd have to somehow make up for that missing energy somewhere along the way. But none of these parts of the interior of the sun are hot enough for fusion. That doesn't make sense either. The only thing that does make sense is that if you're producing 4 times 10 to the 26 watts on the outside, you've got to be generating 4 times 10 to the 26 watts on the inside. The star is in equilibrium. Okay, let's imagine that we considered fusion for just 1 second at the core of the sun. Fusion proceeds by the legendary formula E equals mc squared, where mass is converted into energy. In 1 second, how much mass is, I don't want to say destroyed, I'll say converted? Well, in 1 second, I produce how much energy, class? How much energy am I producing in 1 second, students?
4 times 10 to the 26.
Joules, right?
Yes.
And we'll divide that by the speed of light, 3 times 10 to the 8 meters per second, and we'll square it. What's that get? I'm waiting.
4.4 times 10 to the 9.
4.4 billion. And what are my units? Oh, that's a little better.
Kilograms?
Right. Okay, but isn't it true that that's 4.4 billion kilograms in 1 second, right?
Yeah. So it would be kilograms per second?
Yeah, that's my point. Let's go back up to the top here. And let's argue that the mass loss rate at the core of the sun, sorry, you know what? This marker's kicked. Get rid of that guy. Is 4.4 billion kilograms per second. Now, is that the answer to my question, or do I need to do more?
We need to compare to Earth's mass, right?
But that's not a mass, that's a rate. You're missing something. What am I missing? So I'm working on my lighting while I wait for you guys to figure it out. I think that's pretty uniformly illuminated now. All right, talk to me.
Well, it says that it wants us to estimate how much mass it loses during its 10 billion year life. So we need to figure out how much that is if it's with that number.
Okay, I like what you're saying to me. This all sounds good. So what do I do? I'm still too dumb to understand. I need you to walk me through this. I'm so happy with my lighting right now. That's all I can really think about. I should have done this days ago. Well, how many years was it again?
10 billion.
Okay, so what do I do?
Dimensional analysis?
All right, I like the sound of that. Let's kick it off, Jace. 4.4 billion kilograms per second. What do I do now?
Multiply by division bar.
Okay.
Would you put seconds on the bottom? Or no, on top?
Okay, and then what do I put on the bottom? The problem was not how much mass does the sun lose in 1 second.
Kilograms?
Well, then you'll have nothing. The goal isn't to destroy all units. What should the final answer be? I think you guys have forgotten the question. Y'all on baby bird mode. I need you to be on predator mode, okay? I need you
Final answer should be in kilograms, right?
Right. So I don't think we should cancel out those kilograms. How much
Could we put the life?
Oh.
Could we put the lifetime of the sun on the bottom?
What is the lifetime of the sun?
It's still just time.
No, no. What's the number? What's the value?
9.5 times 10 to the 9.
Or they said we can use 10 billion in this problem. Let's do this. 10 billion years. But what's our problem here? Now our units are kilogram years per second. Damn, y'all stumped. I stumped you.
Should we divide by some unit of time?
Well, you got a unit of time. 10 billion years.
We're trying to get rid of the units of time, though.
All right, so how are you going to do that?
So I'm trying to figure out.
Guys, I can't start drinking until you solve this problem. Okay? So this real stakes here. Real stakes. Oh, hey, Jillian says, convert 10 billion years to seconds. Brilliant. Brilliant idea, Jillian. Way to go. Feel free to talk to us, too. We get lonely, okay? All right, so what am I going to do? All right, so Jillian has the secret. Jillian says convert 10 billion years to seconds. So what do I do?
Multiply by division bar.
Yep.
Years on bottom, seconds on top.
What's my conversion?
1 year is 3.15 times 10 to the 7 seconds.
Nice. Punch them up.
Go 1.4 times 10 to the 27
Units.
kilograms.
Great. There's our answer, but we have to compare this to Earth, okay? We're going to divide the mass loss by the mass of Earth because this number is greater than the mass of Earth. 1 times 10 to the 27 kilograms over 6 times 10 to the 24 kilograms. Another marker's dead. All right. What do you got? Hey, remind me to get markers at CVS when we go there. I'm so pleased with my lighting.
$300, 231.
And what are your units?
No units.
Yeah. It's basically 230 times the mass of Earth. It's approximately equal to the mass of Jupiter. Basically, over the course of 10 billion years, the sun will destroy a Jupiter's worth of matter and convert it into photons, which will take the form of sunshine. And I believe that's the end of our problems. Well, maybe not the end of our problems, but at least the end of our homework, right?
On that last formula,
Say that,
on
Ernie?
the last formula where it says compare to Earth, you have
Yes.
1 to the 27th. It should be 1.4.
Oh, thanks. Thanks, Ernie.
Oh, thank you.
I lost track of that here. Good call. And that's important for everyone following at home too. Cool. Let's get back to gallery view for a second. Let me back this thing up. Woo. Oh my gosh, we almost had a big whoopsie there. Okay. Well, you've successfully wasted another Wednesday talking to me about the sun. We're all going to remember to turn this stuff in proper form, right? JPEGs, PDFs, things I can read. Okay. I'm talking to all you other kids out there that I don't normally get to see or hear from. Make sure you keep up with your work. Any other comments or thoughts? I wonder how we got Zoom bombed. That was pretty crazy, right? Does that guy just go on Zoom like looking for hotlines to crash or? Do you think it was an inside job? That's what I want to know.
You get the password.
Do you
I
guys
feel
have
like it was an inside
password?
job.
No, I don't need the password. I just put
Say that, Laura?
I said, I feel like it's an inside job because I need a password to get in. So I'm like, how did he know? And
But-
he was like on it with the astronomy stuff, you know? He had those questions ready.
Yeah. Well, yeah. So Aiden is a student in our class. That's why when someone logged in as Aiden, I thought it was the Aiden who never logs into class. But he had his eyeballs kind of below the screen there. But so Ernie, you don't need. So I always send you guys the password and the link, but I never know if you need the password. Ernie,
No,
you do not need the password, do you?
just put the URL in and it goes right to you.
But why do? But Laura, you do need the password.
Yeah, I don't know why, but I've always had to put it in.
In fair disclosure, I should let you guys know, you remember my friend Zaz from Australia came on. He's like a data security expert, really smart dude, and a great friend. And he's really against Zoom. He thinks it's a terrible platform because he thinks that the company, once you install their software, they can collect your data, monitor it, sell it, do a lot of things that you probably wouldn't feel 100% comfortable with. Now, I don't want to be lame and use Zoom, but you guys can tell, especially during our labs, that I make extensive use of that iPhone connection. That's really helpful for me because otherwise it's kind of hard to do a good lab if you're just talking. You kind of have to like take some measurements. And since you guys can't be physically present with me anymore, I feel like taking my camera around, you're kind of like my little flying drone eyeball, and you can help me do measurements. And it's crude, but it kind of seems to work. So I really love that feature, and I'm loath to give it up. I also like how I can share my screen and the sound and do all the normal tricks I like to do. Now, there's probably other programs out there that do this, and I should take some time looking into it. But I feel kind of guilty because Zoom is just working, and so it's also recording the lectures, and I'm like, screw it, it works. I don't want a headache here, right? But I heard that the state of New York banned Zoom for all of their college classes. I don't know if that's eventually going to happen here in Rhode Island as well, but I hate to say it, even if Zoom is evil, they're a pretty successful evil, because in one-stop shopping, I can lecture to you, I can record it, I can share my iPhone, and I can share my screen. I don't know. I'm just kind of rambling here, but I did want you guys to know that Zoom, people have issues with it, and you deserve to be aware of it. Zaz sent me a suggestion. He said that I look into well, he had a suggestion for another. He said Jitsi, Jitsi. So I'll try to look into Jitsi. Oh, sorry, Matthew. Let me go back to speaker view. Matthews, does that help, buddy? All right. So does anyone have any comments or questions for me? Anything that we need to talk about, or are we kind of good here for the day?
Enjoy your drink.
Yeah, exactly.
Mine.
Okay. Hey, Matthew, are you good now? Can I go back to gallery mode before I end it? You got that, Matthew? Yes. Okay, cool. So let me do a couple of things before we officially end. Gallery view. Let me save the chat log, because the chat log is not only funny, but maybe helpful in the future. And I'll stop the recording, and then we will end our class. So goodbye.